There exists a world beneath the waves that our eyes cannot see. A universe so vast, so teeming with life, that it defies comprehension. In a single cup of seawater, the amount you might scoop in your hands swim more living creatures than there are people on Earth. This is the realm of Plankton, the invisible rulers of our planet, and their story begins 3.8 billion years ago. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Picture, if you will, the Earth as it was then. No continents as we know them, no blue skies. The atmosphere, a toxic brew of methane and ammonia, would kill you in seconds. Yet in the warm, mineral-rich waters of the primordial ocean, something miraculous was stirring. The first photosynthetic bacteria, ancestors of all plankton, had just discovered the most transformative trick in the history of evac life. They had learned to eat sunlight. These pioneers were unimaginably small. If you could shrink yourself down to their scale, a raindrop would seem like an ocean. Yet what they lacked in size, they made up for in numbers. They multiplied and multiplied and multiplied again, until they numbered in the septillions. That's a number so large it loses meaning more organisms than all the stars in all the galaxies we've ever observed. Each one a tiny factory, converting solar energy into the stuff of life. Consider for a moment what this meant. For the first time in Earth's history, life was no longer confined to volcanic vents and chemical seeps. The entire sunlit surface of the ocean, 71% of our planet, had become a vast dining table. And at this table, the plankton began their patient work of transformation. They exhaled oxygen as waste. At first, this oxygen was absorbed by iron in the oceans, creating vast deposits of rust that we can still see today in ancient rocks. But the plankton kept breathing, kept multiplying, kept pouring oxygen into the water and air. Over hundreds of millions of years, they changed the very chemistry of our planet. The poisonous atmosphere became breathable. The stage was set for complex life. Now let us leap forward in time past the evolution of complex cells, past the Cambrian explosion, past the rise and fall of countless species, to a moment just 180 years ago. The year is 1844. In the harbour of Helgoland, a small German island in the North Sea, a physician named Johannes Müller is about to change how we see the ocean forever. Müller was curious about the murky quality of seawater. Why, he wondered, was the ocean not crystal clear like a mountain spring? He fashioned a cone of the finest silk gauze mesh, so fine it could trap particles smaller than the width of a human hair, and lowered it into the water. What he hauled up would have seemed like magic to anyone watching. Imagine his astonishment as he peered through his microscope at the contents of that net. Here were creatures of impossible beauty, shells of glass twisted into perfect spirals, translucent bells pulsing with life, organisms shaped like stars and crescents and chains. Some sparkled like jewels, others moved with purpose, propelling themselves with whip-like tails or rows of beating cilia. In that single scoop of water, Müller had discovered an entire ecosystem in miniature. Word of his discovery spread through the scientific community like wildfire. Soon, researchers across Europe were dragging silk nets through their local waters, each revealing new wonders. They gave these drifting organisms a name, plankton, from the Greek word planktos, meaning wanderer. It was a poetry that captured their essential nature. Life at the mercy of currents, forever drifting, forever travelling. But the true scope of plankton's dominion would not be revealed until the voyage of HMS Challenger, beginning in 1872. This converted warship, bristling with scientific equipment instead of cannons, embarked on a 3.5-year journey that would cover 70,000 nautical miles. At each of their 362 stations, the scientists lowered their nets not just at the surface, but deep, sometimes 4,000 meters down into the perpetual darkness of the abyss. What they found challenged everything marine biologists believed about the ocean. Plankton were not confined to the sunlit surface waters. They inhabited every cubic meter of the ocean, from the warm tropical seas to the ice edge of Antarctica, from the surface to the deepest trenches. Even in the abyssal depths, where the pressure would crush a human body in milliseconds, plankton thrived. Species unknown to science emerged from every net, thousands of them, each adapted to its particular niche in the three-dimensional wilderness of the sea. The Challenger, Expedition's 50-volume report, which took 23 years to compile, catalogued over 4,000 new species. Yet this was merely scratching the surface. Marine biologists realized they had discovered not just a few new organisms, but an entire parallel world. A world where the rules were different, where being small was an advantage, where drifting was not weakness but strategy. Think about what it means to be plankton. You are so small that water feels thick, like syrup. Swimming any distance requires enormous effort. Imagine trying to do the butterfly stroke through honey. Gravity barely affects you. You're more influenced by the molecular forces of the water itself. In this alien physics, plankton evolved solutions we're only beginning to understand. Some grow spines to increase drag and slow their sinking. Others store oil droplets to boost buoyancy. Many form chains or colonies, creating structures that catch currents like underwater sails. As microscopes improved through the 20th century, each increase in magnification revealed new layers of complexity. What appeared as specks of dust to Muller revealed themselves as architectural marvels. Diatoms, single-celled algae, construct shells from pure glass, each species following its own blueprint with mathematical precision. Coccolithophores armor themselves in plates of calcium carbonate, arranged in patterns that would make a master jeweler weep with envy. Dinoflagellates, when disturbed, produce bursts of blue light using the same chemical reaction that makes fireflies glow. But the most astounding discovery was yet to come. In 1988, two oceanographers, Sally Chisholm and Robert Olson, were testing a new instrument in the Sargasso Sea. This device could detect and count individual cells by making them fluoresce under laser light. What they found revolutionized our understanding of ocean life. Swimming in every milliliter of seawater were hundreds of thousands of organisms smaller than anyone had imagined possible. These were Prochlorococcus, a cyanobacterium so tiny that 100 of them could line up across the width of a human hair. Yet despite their minuscule size, or perhaps because of it, they turned out to be the most abundant photosynthetic organism on Earth. Listen to this carefully, for it's one of those facts that shifts your entire perspective. Prochlorococcus produces 20% of the oxygen in our atmosphere. 1 in every 5 breaths you take comes from an organism you cannot see, had never heard of until recently, and which lives its entire life in a realm beyond your perception. There are 3 octillion of them in the ocean. That's 3 followed by 27 zeros. Together, they perform more photosynthesis than all the rainforests on land. The discovery of Prochlorococcus was like finding a new continent, not of land, but of life itself. It forced scientists to reconsider everything they thought they knew about ocean productivity. If organisms this important could hide from us until 1988, what else was out there? We now know that the ocean contains more life than we ever dreamed. Not just more organisms, but more kinds of organisms. A single liter of seawater may harbor tens of thousands of different species, bacteria, archaea, protists, larvae, eggs, spores. Each has its role in the endless recycling of nutrients that keeps our planet alive. The plankton are not just passengers in the ocean, they are the ocean, as fundamental to its nature as salt or waves. And here's what truly takes my breath away. This invisible world, this universe of drifters, began with those first photosynthetic bacteria 3.8 billion years ago. Through all the mass extinctions, the ice ages, the asteroid impacts that ended the dinosaurs, plankton endured. They adapted, they evolved, they continued their patient work of maintaining the atmosphere, feeding the food chains, building the very rocks beneath our feet. When you stand at the edge of the sea and breathe in that salt-tinged air, you're breathing the breath of plankton. The oxygen filling your lungs, the clouds gathering on the horizon, even the limestone cliffs you might be standing on, all are gifts from the invisible ocean. We live on a plankton planet. We always have. We just didn't know it. As night falls across the ocean tonight, something remarkable is about to begin. The greatest migration on Earth is starting, and it happens every single day. 10 billion tons of zooplankton are beginning to rise from the depths, following a rhythm older than the continents themselves. But that is a story for tomorrow. As the last rays of sunlight fade from the ocean surface, a signal spreads through the depths. It's not a sound or a chemical message, but something more fundamental, the absence of light itself. And in response to this ancient cue, 10 billion tons of life begins to move upward. Every single night, in every ocean across our planet, the greatest migration on Earth is underway. Imagine, if you can, the sheer scale of this movement. More living creatures are traveling right now than all the wildebeest in the Serengeti, all the caribou in the Arctic, all the migrating birds in the sky combined and multiplied 1,000,000 times over. Yet this spectacular journey unfolds in complete silence, hidden from our view by the veil of dark water. To understand this nightly ballet, we must travel back 500 million years to the Cambrian period. Picture the ocean then, a more dangerous place than any modern sea. The first complex eyes had just evolved, and with them came a revolution in the rules of survival. Suddenly, predators could see their prey from a distance. The transparent bodies that had served plankton so well for billions of years became a liability in the bright surface waters. The solution was elegant in its simplicity. Hide in the darkness by day, feed at the surface by night. This behavioral innovation spread through the planktonic world like wildfire. Those who migrated survived. Those who didn't became food. Over millions of generations, this daily rhythm became encoded in their very DNA, a genetic metronome that beats in time with Earth's rotation. Now, let us shrink ourselves down and join this migration as it begins tonight. We find ourselves 600 feet below the surface, in a twilight world where the last photons of sunlight struggle to penetrate. The water here is cold, perhaps 4 degrees Celsius, and the pressure would rupture our eardrums in seconds. But for the zooplankton gathering around us, this is home. Here's a copod, no larger than a grain of rice. Through our magnified view, we can see its transparent body, its feathery antennae sampling the water, its compound eyes scanning for danger. As darkness falls, something remarkable happens inside its tiny nervous system. Specialized cells that detect light photoreceptors more sensitive than any camera register the change. A cascade of hormones floods its body. Its swimming legs, which have been barely moving all day, suddenly spring into action. Watch closely now. The copepod begins to beat its swimming legs in a rhythmic pattern: stroke, stroke, glide, stroke, stroke, glide, to move upward through water that feels as thick as molasses to such a small creature. It must pump its legs 10,000 times. That's equivalent to a human doing 10,000 pull-ups to climb a rope 3,000 feet high. Yet this microscopic athlete will complete its journey in under an hour. All around us, billions of other creatures are beginning the same journey. Krill, those shrimp-like creatures that feed the whales, swim upward in dense swarms. Their movements so coordinated they create currents in the water. Tiny jellyfish, some no bigger than the head of a pin, pulse their bells in a hypnotic rhythm. 18 beats per minute, as regular as a metronome, each contraction pushing them a few millimeters higher. But perhaps the most spectacular migrants are the lanternfish. These finger-sized fish possess organs called photophores, biological light bulbs, that they can switch on and off at will. As they rise, they create underwater constellations, patterns of blue-green light that serve as both communication and camouflage. From below, their lights blend with the stars and moon filtering through the water. From above, they're invisible against the dark depths. The migration routes are as precise as any highway. Using sophisticated sonar, scientists have mapped these vertical roads through the ocean. They appear on instruments as distinct layers, rising and falling with mathematical precision. Some species travel from 3,000 feet deep to just below the surface, a journey that, adjusted for their size, would be like a human walking from New York to Los Angeles. And they do it twice every day. The timing is exquisite. Different species begin their ascent at different moments, creating waves of life moving upward. The first wave consists of the smallest zooplankton, the copepods and larvae. 30 minutes after sunset, the medium-sized creatures follow. An hour after sunset, the predators begin their climb, following the buffet that rises ahead of them. Consider what drives this extraordinary behavior. These creatures have no weather forecasts, no clocks, no GPS. Yet a copepod in the Pacific rises at the same moment relative to sunset as its cousin in the Atlantic. How do they know? The answer lies in an internal clock so precise it rivals atomic timekeepers. Inside each migrator, whether a microscopic copepod or a hand-sized jellyfish, specialized proteins track the passage of time. These molecular clocks, refined over hundreds of millions of years, tick in harmony with Earth's rotation. They can detect changes in day length as small as minutes, allowing plankton to adjust their migration schedule with the seasons. In Arctic waters, where summer brings perpetual daylight, some species switch off their migration entirely, while others maintain the rhythm even without the cue of darkness. But time is only part of the story. These creatures also possess an exquisite sense of depth. They measure pressure with organs so sensitive they can detect the weight of a few centimeters of water. Some species rise to exactly 10 meters below the surface, never 9, never 11, with the precision of a submarine following computer navigation. By midnight, the transformation is complete. The surface ocean, which contained relatively little life at noon, now teems with 10 times, sometimes 100 times more organisms. It's as if an entire city's population commuted vertically instead of horizontally, transforming empty office buildings into bustling nighttime neighborhoods. And what a feast awaits them at the surface. Here, in the top few meters of the ocean, the day-dwelling phytoplankton have been photosynthesizing, turning sunlight and nutrients into food. The ascending hordes fall upon this banquet with voracious appetite. Copepods filter thousands of algae cells per hour through their feeding appendages. Krill sweep the water with their basket-like legs, creating tiny whirlpools that funnel food toward their mouths. Watch this, Chaetognath, an arrowworm as it hunts. Transparent as glass, with grasping spines around its mouth, it hangs motionless in the water. When a copepod swims within range, the arrowworm strikes faster than your eye can follow. In 2 milliseconds faster than a rattlesnake strike, it seizes its prey. All around us, similar dramas play out millions of times per second. The feeding frenzy attracts larger predators from the depths. Lanternfish arrive in schools so dense they show up on sonar as false sea floors. These fish, each no longer than your finger, exist in numbers that defy belief. There are more lanternfish in the ocean than all other fish combined. They've followed the zooplankton upward, and now they feast, their photophores flickering in patterns that identify their species like submarine license plates. But as the eastern sky begins to lighten, another signal spreads through the multitude. Dawn is coming, and with it, danger. The descent must begin. This downward journey is even more remarkable than the ascent, for now the migrants must race against time and their own buoyancy. Watch how different species employ different strategies. Some zooplankton stop swimming entirely, folding their appendages and sinking like tiny parachutes. Others swim actively downward, fighting against their natural tendency to float. The lanternfish dive in spirals, their photophores dimming as they descend. By the time the first rays of sunlight penetrate the surface, most have reached the safety of the twilight zone. But not all make it. Those caught in the light become silhouettes against the bright surface, easy targets for the visual predators now awakening. This merciless selection has shaped the migration for millions of years. The slow are eaten, the quick survive to migrate another night. This great vertical migration serves purposes beyond mere feeding. As the zooplankton gorge at the surface, they package nutrients into their bodies. When they descend, they carry this organic matter into the depths. Their fecal pellets, each a tiny package of carbon and nitrogen, sink even deeper. This biological pump transfers billions of tons of nutrients from surface to deep ocean every year, feeding the creatures of the abyss and storing carbon away from the atmosphere. The migration highways extend from Arctic to Antarctic, connecting all oceans in a three-dimensional network of movement. A copepod feeding under Arctic ice may share ancestors with one rising beneath tropical stars. The genes that control their migration have spread across all ocean basins, uniting distant populations in a shared rhythm. Scientists studying these migrations have made astonishing discoveries. Some copepods can enter a state called diapause, a kind of suspended animation, and sink to spend months in the deep ocean. Their metabolism slowed to nearly nothing. They time their awakening to coincide with plankton blooms at the surface, emerging from their hibernation exactly when food is most abundant. Other species show even more sophisticated behaviors. Certain jellyfish adjust their migration depth based on the phase of the moon, rising higher during new moons when darkness is complete. Krill in Antarctic waters synchronize their migrations with the seasonal advance and retreat of ice, somehow sensing the changes in light that penetrate even thick ice cover. The precision extends to the microscopic level. Researchers using high-speed cameras have filmed individual copepods and discovered that they can adjust the power of each swimming stroke based on water density. In colder, denser water, they beat harder. In warmer surface waters, they modify their rhythm. It's like watching a mountain climber automatically adjust their pace for altitude, except these climbers are smaller than rice grains and have no conscious thought. 20 minutes. That's how fast some of the champion migrators can travel from deep water to surface, a speed that would be like a human running straight up a 70-story building. Others take a more leisurely 3 hours, stopping to feed at different depths along the way. Each species has found its niche in this vertical ecosystem, its own schedule and route through the water column. As our night of observation ends and dawn breaks across the ocean, we're left with a profound realization. This migration, invisible to us surface dwellers, may be the most important animal movement on our planet. It drives ocean productivity, shapes marine food webs, and even influences Earth's climate. Every night, in every ocean, this ancient ballet continues a pulse of life that has beat steadily for 500 million years. Tomorrow, we'll discover how some of these migrants create their own light and build houses of pure glass. We'll enter a world where single cells construct architectural marvels and living creatures glow with cold fire. But tonight, as you sleep in your bed, remember that beneath the waves, billions upon billions of tiny travelers are making their nightly journey, following a rhythm older than the continents, maintaining the ocean's heartbeat with their ceaseless motion. The greatest migration on Earth requires no maps, no leaders, no conscious thought, only the ancient wisdom encoded in DNA, the pull of darkness and light, and the eternal promise of food waiting at the surface. In their endless cycling between depth and surface, the plankton remind us that life's most important journeys are often the ones we cannot see. In a single drop of seawater, suspended like a jewel on the tip of an eyedropper, an architect is at work. This architect has no blueprint, no tools, no conscious thought, yet it builds with a precision that would humble the designers of our greatest cathedrals. It is a diatom, and it constructs its home from glass. Hold that drop up to the light. What appears to the naked eye as mere water contains wonders beyond imagination. Each diatom, a single-celled alga, lives within a shell of pure silicon dioxide, the same material we use to make windows and computer chips. But while our glassmaking requires furnaces burning at 1500 degrees Celsius, diatoms build their houses at the temperature of seawater, using only the dissolved silica around them and the molecular machinery within their cells. The construction process defies belief. Watch through the microscope as it unfolds. First, the diatom absorbs silicic acid from the surrounding water through specialized transport proteins. Inside the cell, in a compartment called the silica deposition vesicle, something miraculous happens. Protein templates arrange themselves into precise patterns, spirals, stars, hexagons, triangles. The silica molecules, guided by forces we're only beginning to understand, align along these templates like iron filings following magnetic field lines. Layer by layer, atom by atom, the glass shell takes shape. The process is so controlled that each species of diatom produces its own distinctive design, as unique as a fingerprint, as consistent as a snowflake. Some create circular shells decorated with pores arranged in perfect mathematical spirals. Others build elongated cases that look like tiny boats, complete with keels and ridges. Still others form chains, each cell's shell interlocking with its neighbors like microscopic freight trains. Consider the numbers. Scientists have identified over 100,000 distinct diatom designs. Each pattern has been encoded in DNA and refined over 200 million years of evolution. These are not random shapes but sophisticated solutions to the challenges of life at microscopic scale. The pores aren't merely decorative, they're precisely sized to allow nutrients in while keeping predators out. The ridges and spines increase surface area for nutrient absorption while providing structural strength. During a diatom bloom, when conditions of light and nutrients align perfectly, 20 million of these glass houses can crowd into a single liter of water. Imagine 20 million architects working simultaneously in a space the size of a large soda bottle, each building a unique structure, none interfering with another. The bloom can turn entire bays into living kaleidoscopes, the water shimmering with billions of glass shells catching and refracting light. But diatoms face a peculiar challenge. Glass doesn't grow. Once a diatom has built its shell, it's locked inside like a medieval knight in armor. How then does it reproduce? The answer is ingenious and slightly absurd. When ready to divide, the diatom splits in two, with each daughter cell keeping half the original shell. One gets the top, one gets the bottom. Each then constructs a new half to complete its house. Here's the catch. The new half must fit inside the old half, like a box and its lid. This means one daughter is slightly smaller than the parent. When it divides, one of its daughters is smaller still. Generation by generation, the diatoms shrink like Russian nesting dolls. Eventually, they become so small they can barely function. That's when they play their trump card sexual reproduction, which allows them to break free from their glass prisons and start again at full size. The glass itself is a marvel of engineering. Diatom shells are stronger than steel when adjusted for weight, yet delicate enough to shatter at a touch. They're riddled with pores that follow mathematical rules, the same patterns that appear in soap bubbles and honeycombs, shapes that achieve maximum strength with minimum material. Nature discovered these optimal forms hundreds of millions of years before human mathematicians proved their efficiency. But glass houses are only part of Plankton's architectural story. As night falls, we witness an even more spectacular display. The water begins to glow, a wave breaks, and blue fire traces its curve. A fish darts through the water, leaving a comet trail of light. A hand swept through the sea creates a galaxy of blue stars. This is bioluminescence living light, and it's one of the ocean's most ancient and sophisticated defense systems. The masters of this cold fire are the dinoflagellates, single-celled organisms that blur the line between plant and animal. By day, many photosynthesize like plants. By night, they produce light like deep-sea creatures. But unlike the steady glow of a lanternfish, dinoflagellate light comes in brilliant flashes, each lasting barely a tenth of a second. Let me show you how this living firework works. Inside each dinoflagellate float thousands of tiny compartments called scintillions. These microscopic packets contain two chemicals, luciferin and luciferase, the same combination that makes fireflies glow. But here's the remarkable part. The chemicals are kept separate by a pH barrier. The luciferin sits in acidic conditions where it cannot react. The luciferase waits outside, ready but powerless. When something disturbs the dinoflagellate, the bow wave of an approaching copepod, the turbulence from a fish's fin channels in the cell membrane open. Protons rush in, acidifying the entire cell in milliseconds. This pH change breaks down the barriers in the scintillons. Luciferin meets luciferase, and chemical energy transforms into blue light in one of the most efficient reactions known to biology. Nearly 100% of the energy becomes light, compared to an LED bulb's 30% efficiency. The flash serves as a burglar alarm. That copepod approaching in the darkness, hoping for an easy meal, suddenly finds itself illuminated in a blue spotlight. To larger predators lurking nearby, it's like a neon sign saying, "Eat me." The copepod usually flees, and the dinoflagellate survives. It's a defense system so effective it has evolved independently at least 40 times in different plankton lineages. Some dinoflagellates have refined this defense to an art form. Noctiluca scintillans, the name means nightlight, can produce 60 flashes per second when disturbed. Each flash uses only a tiny fraction of its chemical reserves, allowing it to keep signaling for hours. During massive blooms, billions of Noctiluca can turn breaking waves into waterfalls of blue flame, visible from space as ghostly rivers of light along coastlines. The light show reaches its peak in places like Mosquito Bay in Puerto Rico or the Maldives' beaches, where dinoflagellate concentrations reach extraordinary levels. Every movement triggers an explosion of light. Swimming becomes like moving through liquid starlight. Fish leave glowing wakes. Diving birds emerge from the water, outlined in blue fire. It's beautiful beyond words. But remember, each flash is a tiny creature's desperate attempt to avoid being eaten. The bioluminescent system is so sensitive, it can detect the minute pressure waves created by approaching predators. Researchers have filmed copepods hunting dinoflagellates in slow motion, revealing an arms race of physics and chemistry. The copepod creates a feeding current to draw prey toward its mouth. But this current pushes a pressure wave ahead, reaching the dinoflagellate 3 milliseconds before the copepod arrives. 3 milliseconds, that's faster than a human blink, yet it's enough time for the dinoflagellate to flash its alarm. But plankton architecture extends beyond glass and light. Let me introduce you to the coccolithophores, perhaps the most prolific builders in Earth's history. These single cells surround themselves with plates of calcium carbonate called coccoliths. Imagine a microscopic suit of armor made from interlocking shields. Each shield is sculpted with species-specific patterns, some like tiny hubcaps, others like delicate flowers, still others resembling microscopic steering wheels. The construction process would impress any engineer. Inside the cell, in a specialized compartment, calcium and carbonate ions are concentrated to levels that would normally cause spontaneous crystallization. But the coccolithophore controls the process with surgical precision. Protein templates guide crystal growth, creating plates of exact size and shape. When complete, the plates are exported to the cell surface and assembled into perfect spheres, like a three-dimensional jigsaw puzzle that assembles itself. A single Emiliania Huxley, the most abundant coccolithophore, carries about 30 coccolith plates, each taking about an hour to construct. When it divides, it must build new plates for its daughter cells. During blooms, trillions of these organisms work simultaneously, turning entire ocean regions milky white with their calcium carbonate armor. Satellite images reveal these blooms as vast white swirls, sometimes covering areas larger than entire countries. The numbers stagger comprehension. A single bloom can remove 1 billion tons of carbon from the atmosphere in 3 weeks, locked away in calcium carbonate. When coccolithophores die, their plates drift down through the water column like microscopic snow. Over millions of years, these accumulated plates have built geological formations of staggering scale. The White Cliffs of Dover, 400 feet of pure white chalk, consist entirely of compressed coccolithophore plates. Every handful contains billions of these microscopic shields, each one perfect, each one built by a single cell. But perhaps the most amazing builders are the radiolarians and foraminifera. These single-celled protists construct shells of stunning complexity from silica and calcium carbonate, respectively. A radiolarian skeleton looks like a collaboration between a master jeweler and a mathematician. Intricate lattices of glass, following geometric rules that maximize strength while minimizing material. Some resemble microscopic Eiffel Towers. Others look like crystalline snowflakes or delicate Victorian lampshades. The construction techniques vary wildly. Some species build by secreting material along precise lines, like 3D printers working at molecular scale. Others use pseudopodia, temporary extensions of their cell body, to position individual mineral crystals, cementing them in place one by one. Still others create organic templates that mineralize in specific patterns, the living cell orchestrating a symphony of chemistry and physics. Time-lapse photography reveals the construction process as a dance of extraordinary precision. A foraminiferan, adding a new chamber to its spiral shell, first extends its cytoplasm into the exact shape of the future chamber. It then secretes calcium carbonate, starting at multiple points simultaneously. The crystallization fronts advance and meet with micrometer precision, creating seamless walls of perfect thickness. The entire process, from initial extension to completed chamber, takes about 12 hours. These microscopic architects work without blueprints, without nervous systems, without any of the tools we consider essential for construction. Yet they build structures of mathematical perfection, each species faithful to its own design across millions of generations. They've been doing this for hundreds of millions of years, their discarded shells accumulating on the ocean floor, eventually compressed into limestone and chalk that now forms mountain ranges. Living light and glass houses, these are the everyday miracles of the planktonic world. In each litre of seawater, thousands of architects work in glass and calcium, building structures that combine beauty with function. When darkness falls, that same water may burst into blue flame at the slightest touch, each flash a testament to the chemical sophistication of organisms we can barely see. Tomorrow, we'll discover that these same waters are also battlegrounds, where microscopic wars rage with chemical weapons more sophisticated than anything in human arsenals. We'll meet the organisms that produce the most powerful toxins on Earth and learn how their invisible conflicts shape the entire ocean ecosystem. But tonight, as you imagine the sea, picture it as it truly is, filled with glass palaces and living stars, a universe of builders and light makers pursuing their ancient crafts in the darkness between waves. In a teaspoon of seawater, a war rages. Not a war of territory or resources in any way we might recognize, but a conflict fought with molecules, waged at speeds that defy perception. 10 million viruses lurk in that single spoonful, hunting their prey with relentless precision. Their targets, the plankton, respond with chemical weapons more sophisticated than anything in human military arsenals. This is nature's arms race at its most fundamental level, where survival depends on split-second chemistry and evolutionary innovation. Let me paint you a picture of this invisible battlefield. A copepod, our rice grain-sized predator, swims through the water, its feeding appendages creating currents to draw in prey. But physics betrays its presence. As it moves forward, it pushes a bow wave ahead, a pressure signal that races through the water faster than the copepod itself. For a human-sized predator, this would be inconsequential. But at the microscopic scale, where water feels thick as honey, this bow wave becomes an early warning system. A dinoflagellate detects the approaching pressure wave. In 3 milliseconds, 3/1000ths of a second, it must react or be consumed. Chemical cascades explode through its single cell. Ion channels slam open. In specialized compartments, enzymes that have been waiting in dormant readiness suddenly activate. The dinoflagellate begins producing saxitoxin, a neurotoxin so potent that a few millionths of a gram can kill a human. Think about what this means. An organism without a brain, without specialized tissues, without anything we might recognize as a weapons factory, manufactures one of the most deadly substances known to science. Saxitoxin blocks sodium channels in nerve cells, causing paralysis and death. It's 1,000 times more poisonous than cyanide, and this single-celled organism produces it from scratch in less time than it takes you to blink. The copepod's chemoreceptors, imagine microscopic taste buds on its antennae, detect the toxin and trigger an escape response. It reverses direction with a powerful stroke of its swimming legs, fleeing the poisonous cloud. The dinoflagellate survives another encounter, but the chemical traces linger in the water, a molecular minefield that warns other predators of danger. This scenario plays out millions of times per second in every drop of ocean water, but saxitoxin is just one weapon in plankton's vast chemical arsenal. Let me introduce you to some others. When certain diatoms detect the saliva of grazing copepods, yes, they can taste their predator's spit. They undergo a transformation that seems impossible. Within 6 hours, they grow spines. Not over generations through evolution, but in real time. The same individual diatom that was smooth-shelled this morning becomes a spiky fortress by evening. The genetic machinery for spine production lies dormant until triggered by the specific chemical signature of predator presence. The chemistry involved is breathtaking. The diatom's chemical sensors detect copepod-specific molecules in concentrations as low as a few parts per trillion. That's equivalent to detecting a single drop of a substance dissolved in 20 Olympic swimming pools. Upon detection, gene expression changes dramatically. Proteins that were being produced for routine cellular maintenance suddenly stop. Instead, the cell redirects its entire molecular machinery towards spine construction. But predators have their own chemical weapons. Some copepods produce enzymes that break down diatom toxins, turning poisons into harmless byproducts. It's like carrying universal antidotes. Other zooplankton have evolved even more sophisticated defenses. They steal their weapons from their prey. Watch this nudibranch, a tiny sea slug no bigger than a rice grain, as it feeds on toxic dinoflagellates. Instead of being poisoned, it incorporates the dinoflagellate's toxin-producing cells into its own body. The stolen cells, called kleptocnidae, continue producing toxins, now defending their new host. It's biological piracy at the cellular level. Why evolve your own chemical weapons when you can steal them from your food? The arms race extends to every aspect of Ovis Essex, planktonic life. Some phytoplankton produce compounds that prevent their DNA from being copied, effectively sterilizing the viruses that infect them. Others manufacture molecules that cause predator eggs to develop abnormally, reducing the next generation of grazers. Still others release chemicals that attract the predators of their predators. Imagine if grass could summon wolves when rabbits start grazing. One of the most diabolical strategies belongs to certain species of Pseudonitskia, a diatom that produces domoic acid. This neurotoxin causes amnesia in vertebrates, hence the name amnesic shellfish poisoning in humans who eat contaminated seafood. But here's the sinister part. Domoic acid also acts as a chemical attractant for copepods. The diatoms literally drug their predators into eating more, even as the toxin accumulates in the copepod's body. Eventually, fish eat the poisoned copepods, and the toxin moves up the food chain, sometimes killing sea lions and dolphins that feed on the contaminated fish. The speed of these chemical transformations challenges our understanding of biology. When the colonial algae Phaeocystis is attacked, it can shift from toxin production to releasing massive amounts of dimethyl sulfide in under a minute. This compound doesn't just repel predators, it rises into the atmosphere, where it triggers cloud formation. The clouds reflect sunlight, cooling the ocean surface. A microscopic alga, when threatened, can literally change the weather. But perhaps the most remarkable chemical defense belongs to certain dinoflagellates that produce brevetoxins. These molecules don't just poison predators, they reprogram their nervous systems. Exposed fish swim in circles, unable to maintain balance. Their gills hemorrhage. Their behavior becomes so erratic that fishermen can spot a toxic bloom by watching for fish swimming upside down at the surface. What makes brevetoxin truly extraordinary is its molecular architecture. It's a ladder-shaped molecule with 11 rings, so complex that chemists took decades to understand its structure. Each ring must be in exactly the right position for the toxin to work. Change a single atom, and it becomes harmless. Yet dinoflagellates build this molecular masterpiece from simple carbon, hydrogen, and oxygen, using enzyme systems that would be the envy of any pharmaceutical company. The bacterial world adds another layer to this chemical warfare. Marine bacteria produce an astounding variety of antibiotics, antifungals, and anti-predator compounds. Some release molecules that jam the communication systems of other bacteria. Imagine warriors using chemical static to block enemy radio communications. Others produce surfactants that break down the protective biofilms of competing species, like molecular battering rams. Viruses, despite being non-living packets of genetic information, are master manipulators of this chemical battlefield. Some carry genes for toxin production, which they insert into their bacterial hosts. The infected bacteria become poison factories, killing competing bacteria and releasing more viruses when they burst. Other viruses carry genes that make their hosts invisible to predator chemoreceptors, molecular cloaking devices written in DNA. The detection systems are equally sophisticated. Plankton don't just react to chemicals, they analyze them. A copepod's chemoreceptors can distinguish between hundreds of different molecules, identifying not just what species of phytoplankton are present, but their nutritional status, stress level, and toxicity. It's like having a chemical laboratory on your antennae, capable of instant analysis at molecular concentrations. Some organisms take chemical communication to extraordinary levels. Certain bacteria release molecules called autoinducers that allow them to count their own population density. When the crowd reaches a critical threshold, a phenomenon called quorum sensing, coordinate their behavior, simultaneously producing toxins or light or other compounds. It's bacterial democracy through chemistry, decisions made by molecular vote. The consequences of these microscopic wars ripple far beyond the combatants. When toxic dinoflagellates bloom, their poisons accumulate in filter feeders like shellfish. A single mussel can concentrate toxins to levels millions of times higher than in the surrounding water. Months later, a human eating that mussel can die from paralytic shellfish poisoning, killed by a chemical conflict between organisms they never knew existed. Red tides, massive blooms of toxic dinoflagellates, can devastate entire coastal ecosystems. The toxins become aerosols, carried inland by wind, causing respiratory problems in humans miles from the beach. Fish kills number in the millions. Marine mammals, confused by neurotoxins, beach themselves in groups, all from single-celled organisms defending themselves against microscopic grazers. Yet for all their deadly potential, these chemical weapons serve a greater purpose. They maintain balance in the planktonic ecosystem, preventing any one species from monopolizing resources. The constant threat of chemical attack drives diversity, forcing organisms to continuously evolve new strategies. Today's successful defense becomes tomorrow's evolutionary pressure for better predator detoxification systems. Scientists studying these chemical interactions have made discoveries that benefit humanity. Marine plankton have provided compounds that became anti-cancer drugs, antibiotics, and research tools for understanding nervous systems. The green fluorescent protein, revolutionizing medical research and winning a Nobel Prize, came from a jellyfish. Bryostatin, a potential Alzheimer's treatment, comes from bacteria living on bryozoans. The chemical weapons of plankton's microscopic wars become healing tools in human hands. As our understanding deepens, we realize that the ocean's chemical language is more complex than any human communication system. Every molecule tells a story of predator and prey, of competition and cooperation, of death and survival. In each drop of seawater, thousands of chemical conversations occur simultaneously, a molecular Babel that maintains the ocean's living architecture. The plankton remind us that warfare isn't always about size or strength. Sometimes the most powerful weapons come in molecular packages, deployed by creatures we can barely see. Their conflicts, fought with toxins and chemical signals, shape our ocean's ecology as surely as the migrations of whales or the hunting of sharks. Tomorrow, we'll discover how these tiny warriors, despite their microscopic size, have literally built mountains and carved ocean basins. We'll see how their patient accumulation over billions of years has sculpted our planet's very geology. But tonight, remember that the peaceful-looking ocean is actually a vast battlefield, where chemical weapons more sophisticated than anything in human arsenals are deployed every second in an ancient war that keeps our seas alive. Stand atop the white cliffs of Dover and run your hand along the chalk face. That white powder on your palm? It's the compressed remains of creatures that lived 100 million years ago. Coccolithophores so numerous that their microscopic shells accumulated over millions of years, now rise 400 feet above the English Channel. This is plankton's greatest magic trick, transforming sunlight and seawater into mountain ranges. Let me share a number that shifts perspective entirely. In one handful of Dover chalk, you hold the remains of 100 billion individual organisms. Each was once a living cell, floating in Cretaceous seas, building its calcium carbonate armor plate by plate. When they died, they drifted down through the water column like microscopic snow, accumulating on the seafloor at a rate of about 1 millimeter per century. Patient, inexorable, world-changing. The story of plankton as planetary sculptors begins 3 billion years ago. The first photosynthetic bacteria hadn't yet invented the hard shells that would become their geological calling cards, but they were already transforming Earth through chemistry. As they multiplied in the ancient oceans, they began pulling carbon dioxide from the atmosphere and locking it away in their bodies. When they died and sank, that carbon was buried in seafloor sediments. This process, the biological carbon pump, would become one of the most powerful forces shaping our planet. But the real revolution began about 500 million years ago, during the Cambrian explosion. That's when plankton discovered architecture. They learned to build shells from calcium carbonate and silica, minerals dissolved in seawater. Suddenly, these microscopic organisms weren't just living and dying, they were leaving permanent records, constructing monuments to their existence, one cell at a time. Consider what happens during a modern coccolithophore bloom. Satellite images show these events as vast, milky swirls in the ocean, sometimes covering areas larger than Great Britain. In a single bloom lasting 3 weeks, these organisms can remove 1 billion tons of carbon from the atmosphere. That's equivalent to the annual carbon emissions of 100 million cars, locked away in calcium carbonate shells, each more intricate than any human-carved jewelry. The numbers become astronomical. Every year, coccolithophores produce about 1.4 billion tons of calcium carbonate. Diatoms contribute another 8 billion tons of silica shells. Foraminifera add their share. Over geological time, these contributions accumulate into formations that dwarf any human construction. The chalk beds of Europe, laid down during the Cretaceous period, stretch from England to the Middle East, in some places reaching thicknesses of 1,000 feet. But how exactly do microscopic shells become mountains? Let me walk you through the journey. When a coccolithophore dies in the surface ocean, its coccoliths, those tiny calcium carbonate plates, begin to sink. Each plate is only 3 micrometers across, so light it should float forever. But marine snow changes everything. Dead organisms clump together with mucus, fecal pellets, and other organic matter, forming aggregates heavy enough to sink at rates of 100 meters per day. Picture this descent through the ocean's layers. In the sunlit surface waters, the coccoliths are pristine white, their intricate patterns still perfect. As they sink through the twilight zone, scavengers pick away the organic matter, but the mineral shells remain. By the time they reach the deep ocean, 5 weeks after beginning their journey, they've entered a chemical gauntlet. Deep waters are more acidic, dissolving calcium carbonate. Many shells vanish during this final descent, their atoms returning to the dissolved mineral pool. But in certain places, shallow seas, continental shelves, regions where ocean chemistry favors preservation, the shells survive to reach the seafloor. Here they accumulate, layer upon layer, year after year, century after century. The weight of overlying sediments compresses them. Minerals in the buried shells slowly recrystallize, cementing particles together. What began as loose sediment transforms into solid rock. This transformation from plankton to stone happens everywhere oceans have existed. The limestone formations of the American Midwest, built by plankton in ancient seas, the marble quarries of Italy, metamorphosed plankton shells. their calcium carbonate recrystallized by heat and pressure into the stone Michelangelo carved. The vast Permian Basin of Texas, source of much of America's oil, a plankton graveyard from 250 million years ago. Diatoms write their own geological stories in silica. When conditions favor their preservation, usually in colder waters where silica doesn't dissolve as readily, their glass shells accumulate into deposits called diatomite or diatomaceous earth. These formations can be hundreds of feet thick, composed entirely of microscopic glass boxes. So pure is this accumulation that diatomaceous earth is mined for use in filters, absorbents, and even toothpaste. Every time you brush your teeth with certain brands, you're using the fossilized shells of diatoms. The geological influence extends beyond simple accumulation. Plankton shells carry chemical signatures that preserve ancient ocean conditions. The ratio of different oxygen isotopes in a foraminiferan shell tells us the temperature of the water in which it lived. Analyze shells from different depths in seafloor sediments, and you can reconstruct ocean temperatures going back millions of years. This is how we know that 50 million years ago, during the Paleocene-Eocene thermal maximum, ocean temperatures reached 35 degrees Celsius, warm enough for crocodiles to swim in Arctic waters. The evidence comes from the shells of plankton, each one a tiny thermometer preserving a moment of Earth's climate history. By reading these chemical signals in rocks around the world, scientists have reconstructed the entire history of Earth's climate, ice ages, and warm periods alike, all written in plankton shells. But plankton don't just record history, they make it. The biological pump that transfers carbon from atmosphere to deep ocean has profoundly influenced Earth's climate for billions of years. During the Carboniferous period, massive plankton productivity pulled so much carbon dioxide from the atmosphere that it triggered global cooling and extensive glaciation. The coal deposits we burn today are partly the compressed remains of ancient plankton blooms, carbon captured from the air 300 million years ago. The process continues today at staggering scales. Plankton currently transfer about 10 billion tons of carbon annually from the atmosphere to the deep sea. Without this biological pump, atmospheric carbon dioxide levels would be about double their current values. Earth would be a vastly different planet, hotter, with more extreme weather, possibly uninhabitable for many current life forms. Plankton, through their patient work of growth, death, and sinking, maintain the atmospheric balance that allows complex life to flourish. Some plankton contributions to geology border on the fantastical. Take the phosphorite deposits found on many continental margins. These formed when massive plankton blooms died and decomposed on the seafloor, releasing phosphorus that combined with calcium to form new minerals. Today, we mine these ancient plankton graveyards for fertilizer to grow our food. The wheat in your bread may have drawn its phosphorus from plankton that died 100 million years ago. Or consider the role of plankton in forming petroleum. Deposits. When plankton die in oxygen-poor waters, their organic matter doesn't fully decompose. Instead, it's buried and slowly cooked by geological heat and pressure. Over millions of years, the complex organic molecules break down and reorganize into hydrocarbons, oil, and natural gas. The gasoline in your car, the plastic in your computer, the asphalt on the roads, all are transformed plankton, energy from ancient sunlight captured by organisms too small to see. The sculpting power of plankton extends to the shape of the ocean basins themselves. In regions of high productivity, like the equatorial Pacific, the rain of plankton shells to the seafloor is so intense it builds submarine plateaus. The Ontong Java Plateau, larger than Alaska, rises 2 miles above the surrounding seafloor, built entirely from plankton shells accumulated over millions of years. It's a submarine mountain range constructed by creatures smaller than dust motes. Even more remarkably, the weight of these accumulated shells can depress the ocean floor. Geophysicists have calculated that in some regions, the seafloor has subsided by hundreds of meters under the weight of plankton-derived sediments. The ocean basins we see today, their depth and shape, have been partly sculpted by the patient accumulation of microscopic shells. Recent research reveals that plankton influence geology in ways we're only beginning to understand. Certain bacteria produce minute magnetic crystals, magnetite, that they use for navigation. When these bacteria die, their magnetic crystals are preserved in sediments. These microscopic magnets align with Earth's magnetic field at the time of deposition, recording the history of magnetic pole reversals. Geologists reading this magnetic record in sediments can date rock layers and track the movement of continents, all thanks to magnetic crystals produced by bacteria smaller than a wavelength of light. The limestone caves that attract millions of tourists decorated with stalactites and stalagmites owe their existence to plankton. The original limestone formed from plankton shells. Later, slightly acidic groundwater dissolved channels through the rock, creating caves. The dissolved calcium carbonate then reprecipitated as cave formations. Every limestone cave on Earth is a gallery sculpted from the remains of ancient plankton. As I speak these words, plankton continue their geological work. In the Gulf of California, diatoms are accumulating so rapidly they're forming laminated sediments, alternating light and dark layers that record seasonal blooms like tree rings. In the Bahamas, coccolithophores are building carbonate banks that may become tomorrow's limestone islands. Off Antarctica, the shells of foraminifera are preserving records of our changing climate that scientists thousands of years from now will read like books. This is plankton's deepest magic, the transformation of the ephemeral into the eternal. Organisms that live for days or weeks leave monuments lasting millions of years. Their shells become the stage upon which the drama of evolution plays out. The white cliffs where Darwin pondered natural selection, the limestone peaks where fossils reveal ancient life, the very rocks beneath our feet, all are gifts from the invisible multitudes that drift in every drop of seawater. Tomorrow, we'll explore how these ancient architects are racing against time, evolving in real time to survive in our changing oceans. But tonight, remember this: every limestone building, every marble statue, every chalk drawing is made from plankton. We live in cities built from their bodies, drive on roads paved with their remains, and write our history on paper filled with their fossilized shells. They are the true architects of our world, patient and persistent, building Earth's geology one microscopic shell at a time. In laboratories floating on the world's oceans, an extraordinary race unfolds. Scientists watch through microscopes as plankton evolve before their eyes, adapting to acidifying waters at speeds that challenge our understanding of evolution itself. What Darwin measured in finches over decades, these microscopic organisms achieve in months. They are rewriting the rules of survival in real time, and their success or failure will determine the future of life in our seas. The crisis is stark. Ocean acidification advances at rates unprecedented in 65 million years since the asteroid impact that ended the dinosaurs. As we pump carbon dioxide into the atmosphere, the oceans absorb about 1/4 of it, triggering a chemical reaction that makes seawater more acidic. For plankton that build calcium carbonate shells, it's like trying to construct a house while acid rain dissolves it faster than you can build. Let me share an experiment that reveals nature's ingenuity. In a floating laboratory off the coast of Norway, researchers placed coccolithophores in water matching the pH levels projected for the year 2100. The first generation struggled. Their coccoliths, those intricate calcium carbonate plates, formed slowly, irregularly, some dissolving as fast as they crystallized. Mortality rates soared. It seemed like a death sentence for these crucial organisms. But then something remarkable happened. By the 1000th generation, roughly 3 years for these fast-reproducing organisms, the population had transformed. The new coccolithophores built their shells 30% faster than their ancestors. They had evolved enhanced ion pumps that could extract carbonate from increasingly hostile water. Some had even changed their coccolith architecture, building denser, more dissolution-resistant structures. The speed of this adaptation defies traditional evolutionary thinking. We're watching natural selection compressed into laboratory time, like a film fast-forwarded until individual frames blur into continuous motion. Each generation carries mutations, tiny errors in DNA copying and in the harsh selection pressure of acidified water. Beneficial mutations spread through populations with stunning rapidity. But here's what truly amazes. Some plankton aren't evolving new traits, they're awakening ancient ones. Hidden in their DNA are genes that haven't been expressed for millions of years, genetic memories of past climate crises. When conditions deteriorate, cellular mechanisms activate these dormant sequences. It's as if plankton carry a library of survival strategies, accumulated over 3 billion years, waiting for the right environmental cue to open specific books. Consider the dinoflagellate Alexandrium. When exposed to warming water, certain populations activate genes that produce heat shock proteins, molecular chaperones that prevent other proteins from unfolding in high temperatures. The remarkable part? These genes match those found in dinoflagellates from the Paleocene-Eocene thermal maximum 56 million years ago. The organisms are literally remembering how their ancestors survived the last great warming. The tool that makes this possible is horizontal gene transfer, nature's version of file sharing. Unlike animals that pass genes only to their offspring, plankton can swap genetic material between completely unrelated species. A bacterium develops resistance to acidification, and within months, that genetic innovation spreads to algae, to archaea, to organisms across the tree of life. It's evolution on steroids, adaptation at internet speed. Watch this play out in a single drop of seawater. A cyanobacterium under stress releases vesicles, tiny bubbles of cell membrane containing DNA fragments. These genetic care packages drift through the water until absorbed by other organisms. If the DNA contains useful adaptations, the recipient gains an instant evolutionary advantage. No waiting generations for beneficial mutations, just immediate genetic upgrades, downloaded from successful neighbors. Some adaptations seem to violate logic. Faced with carbonate chemistry that makes shell building nearly impossible, certain foraminifera have abandoned calcium carbonate entirely. They now build shells from organic polymers, essentially switching from limestone to plastic. Others have developed symbiotic relationships with bacteria that create microenvironments of favorable pH, chemical oases, where traditional shell construction remains possible. The most dramatic survival strategy might be cryptobiosis, the ability to enter suspended animation when conditions become unbearable. Arctic plankton demonstrate this with stunning effect. As ice forms, trapping them in frozen seawater, they shut down all metabolic processes. No respiration, no cell division, no detectable life activity. They can remain in this state for up to 500 years. When the ice melts, these organisms revive within hours, resuming life as if no time had passed. They carry their genetic adaptations across centuries, evolutionary solutions waiting in frozen time capsules for conditions to improve. It's a strategy that turns climate change from a death sentence into a temporary inconvenience, at least for species that master this ultimate waiting game. But evolution isn't just about individual survival, it's about ecosystem transformation. As different species adapt at different rates, the entire structure of planktonic communities shifts. Fast-evolving bacteria and small algae gain advantages over slower adapting species. Food webs that have existed for millions of years reorganize in decades. Predator-prey relationships refined over evolutionary timescales must be renegotiated as both partners change. In the Baltic Sea, we're watching this reorganization in real time. Diatoms that once dominated spring blooms now face competition from smaller flagellates better adapted to low pH conditions. The copepods that specialized in eating diatoms must adapt their feeding strategies or face starvation. Fish that depend on copepods must shift their migration patterns. The reverberations cascade through the entire ecosystem. Some plankton hedge their evolutionary bets through phenotypic plasticity, the ability to change their characteristics without genetic modification. The Coccolithophore Emiliania huxleyi can produce different types of coccoliths depending on conditions. In normal seawater, it builds ornate, highly sculptured plates. In acidified water, it switches to simpler, more robust designs. Same genes, different expression, like a musician playing different songs on the same instrument. The race intensifies in polar waters, where acidification proceeds fastest. Cold water absorbs more carbon dioxide, and polar plankton face the harshest conditions. Yet here too, life finds ways to persist. Some Arctic diatoms have evolved antifreeze proteins that prevent ice crystal formation in their cells. Others produce extracellular, polymeric substances, essentially slime, that buffers the pH in their immediate vicinity, creating tiny refuges of hospitable chemistry. Laboratory evolution experiments reveal the staggering potential for adaptation. Researchers have pushed plankton through hundreds of generations under extreme conditions, temperatures that would cook most proteins, pH levels that dissolve shells on contact, toxic metal concentrations that should poison all life. Yet populations survive, adapt, even thrive. The solutions they evolve often surprise scientists: novel biochemical pathways, unprecedented cellular structures, ecological relationships never before observed. One experiment tracked a population of marine bacteria through 2,000 generations of increasing temperature. The final organisms grew optimally at temperatures 12 degrees Celsius higher than their ancestors, a change that would typically take millions of years achieved in just 3 years. They had rewired their entire metabolism, replacing heat-sensitive enzymes with thermostable alternatives, developing new membrane compositions that remained fluid at temperatures that would solidify normal cells. But adaptation has costs. Organisms optimized for extreme conditions often sacrifice efficiency under normal circumstances. A coccolithophore adapted to build shells in acidified water might struggle to compete when conditions improve. Evolution solves immediate problems, not future ones. Today's adaptations might become tomorrow's handicaps. This evolutionary sprint creates what scientists call winners and losers in the climate change lottery. Prochlorococcus, that most abundant photosynthetic organism, appears to be a winner. Its multiple ecotypes, genetic variants adapted to different conditions, provide tremendous flexibility. As oceans warm and stratify, different ecotypes dominate different regions, maintaining overall productivity even as local populations shift. Larger, slower reproducing species. Certain foraminifera that build elaborate, multi-chambered shells simply cannot adapt quickly enough. Their 1,000-year generation times doom them in a world changing by decades. As they decline, they take with them their role in food webs and carbon cycling, losses that ripple through ocean ecosystems. Yet even apparent losers might surprise us. Deep in marine sediments lie cysts and spores of plankton species that vanished from the water column decades or centuries ago. These resting stages can survive extraordinary periods, waiting for favorable conditions to return. Ocean warming might awaken species that have slumbered since the medieval warm period, ancient players returning to a changed game. Scientists racing to decode plankton genetics make discoveries daily. The genome of Emiliania huxleyi contains over 30,000 genes, more than humans possess, providing vast genetic raw material for adaptation. Many genes appear to be evolvability genes, sequences that increase mutation rates in specific cellular systems, allowing rapid evolution where it's needed most while maintaining stability in core functions. The implications extend far beyond the ocean. Plankton produce half our oxygen, drive global nutrient cycles, and regulate climate. Their evolutionary responses to changing conditions will cascade through Earth's entire biosphere. If photosynthetic plankton falter, atmospheric oxygen could decline. If the biological carbon pump weakens, atmospheric carbon dioxide will rise faster. We're not just observing evolution, we're watching the future of our planet unfold in microscope slides. Some researchers propose radical interventions. Could we accelerate beneficial evolution through directed selection? Might we transfer successful adaptations between species more efficiently than nature? These questions move from academic to urgent as the pace of ocean change accelerates. We're simultaneously witnesses to and participants in the greatest evolutionary experiment in 65 million years. The plankton themselves offer no opinions, only responses. They adapt or die, evolve or extinct, their billion-year success story facing its greatest test. In laboratories and oceans around the world, they race against tomorrow with the only tools they've ever had: mutation, selection, and time. Whether they have enough of each remains an open question, one whose answer will shape the future of life on Earth. Tomorrow, we'll complete our journey through the invisible ocean, discovering how these microscopic drifters connect every breath we take to the vast cycles that maintain our living planet. But tonight, as you sleep, remember that in the darkness of the sea, evolution never rests. Millions of microscopic experiments unfold with each cell division, each one a gamble on tomorrow, each survivor carrying hard-won solutions to an uncertain future. Take a breath. In this simple act, performed 23,000 times each day without thought, you connect yourself to the vast machinery of the invisible ocean. Half the oxygen molecules now entering your lungs were created by plankton, perhaps by a diatom drifting in the Indian Ocean, or a cyanobacterium multiplying in the Mediterranean. With every exhale, you return carbon dioxide to the atmosphere, where it will eventually dissolve into seawater and feed the next generation of microscopic drifters. You are, whether you know it or not, part of plankton's planetary circulation system. The numbers that define this relationship stagger comprehension. 100 quintillion plankton organisms drift through our oceans. That's 100 million trillion, a number so vast it loses meaning. If you could count them at one per second, it would take 3 trillion years, more than 200 times the age of the universe. Collectively, they weigh more than all the fish, whales, and squids combined. They are the ocean's true biomass, the foundation upon which all marine life ultimately depends. Yet for all their abundance, each individual plankton lives a life of profound vulnerability. Unable to swim against currents, at the mercy of predators they cannot outrun, dependent on nutrients they cannot seek out, they survive through the only strategy available to the powerless absolute acceptance of forces beyond control. In their surrender to wind and wave, tide and current, they embody life's deepest wisdom: persistence through compliance, survival through surrender. Consider the journey of a single coccolithophore, born in the sunlit waters of the Sargasso Sea. It has no knowledge of its purpose, no awareness of its role in Earth's grand cycles. It simply exists photosynthesizing, building its calcium carbonate armor, dividing when conditions allow. It may live for days or weeks before death claims it, beginning its slow descent to the abyss. As it sinks, this microscopic mote becomes part of marine snow, that gentle, eternal rain of organic matter that feeds the deep ocean. Its body provides nutrients for bacteria in the twilight zone. Its calcium carbonate shell continues downward, perhaps dissolving in the deep waters, its atoms returning to the dissolved mineral pool, or perhaps surviving to join the sediments that will one day become limestone mountains. This single organism's contribution seems insignificant, one snowflake in a blizzard. But multiply its story by the numbers of plankton, by the days in geological time, and you begin to grasp the patient power of the microscopic multitudes. They are Earth's great recyclers, taking the raw materials of existence, sunlight, water, carbon dioxide, minerals, and weaving them into the fabric of life itself. We humans, with our 70-year lifespans and technological ambitions, are newcomers to a planet shaped by plankton patience. They've survived apocalypses that wiped out 90% of species. They've endured ice, ages that locked up the oceans, warming events that turned poles tropical, asteroid impacts that darkened skies for years. Through each crisis, some survived, adapted, and repopulated empty seas. Their survival strategies reveal profound truths about existence. They don't resist change, they incorporate it. When oceans acidify, they evolve new shell-building chemistry. When temperatures rise, they shift their ranges or activate heat resistance genes. When food disappears, they enter dormancy, waiting centuries if necessary for conditions to improve. They teach us that survival isn't about strength or size or intelligence, it's about flexibility, patience, and the willingness to change. In their microscopic bodies play out all the dramas we associate with larger life. They hunt and flee, cooperate and compete, communicate and deceive. They wage chemical warfare with sophistication that humbles our military chemistry. They build architectural wonders that surpass our greatest buildings in precision and beauty. They create light from chemicals, navigate using the sun, and some even harness quantum mechanics to enhance photosynthesis efficiency. Yet they accomplish all this without brains, without nervous systems, without any of the complexity we assume necessary for sophisticated behavior. They remind us that intelligence, as we define it, is just one solution to survival. Their distributed sensing, their chemical communications, their genetic flexibility, these represent alternative forms of problem solving, refined over billions of years. The ocean they inhabit is not the empty water we perceive, but a structured ecosystem as complex as any rainforest. Layers of different communities exist at different depths, each adapted to specific conditions of light, temperature, and pressure. Chemical gradients invisible to us create highways and barriers, territories and neutral zones. Microscopic predators patrol these boundaries while prey species evolve ever more sophisticated defenses. In this liquid universe, size confers disadvantages as often as benefits. Large organisms must work constantly to avoid sinking, while tiny plankton float effortlessly. Big bodies require more food, creating vulnerability during scarcity. Small size allows rapid reproduction, quick evolution, survival through sheer numbers. The meek haven't inherited the earth, they've always owned it. Plankton connect oceans in ways that defy political boundaries and human timescales. A phosphorus atom absorbed by a diatom in Antarctic waters might, over centuries, travel north in the body of a migrating whale, be released off Alaska, incorporated into a coccolithophore, sink to the seafloor, be upwelled off Peru, and begin the cycle anew. They are the original globalists, citizens of everywhere and nowhere. Their influence extends beyond the ocean. Dimethyl sulfide gas released by dying phytoplankton seeds cloud formation, affecting weather patterns thousands of 2 miles inland. The oxygen they produce doesn't respect the boundary between sea and air. It circles the globe, entering lungs in Tibet, New York, the Amazon. Even the limestone and marble in our buildings connect us to ancient seas. every polished surface a window into plankton's deep history. Modern technology reveals new wonders daily. Environmental DNA sampling detects species from single cells in seawater, revealing diversity that explodes previous estimates. Satellite sensors track plankton blooms from space, watching them paint the oceans in swirls of green and white. Genetic sequencers decode plankton evolution in real time, while submarines explore their vertical migrations with sonar that shows living layers rising and falling like slow-motion waves. Yet for all our tools and knowledge, plankton retain their mysteries. We've identified perhaps 10% of species. We understand only fragments of their chemical communications, their quantum biological tricks, their magnetic navigation, their ability to survive extremes. These push the boundaries of known biology. They remind us that nature's creativity far exceeds our imagination. As climate change accelerates and oceans acidify, plankton face their greatest challenge in millions of years. Yet their response reveals not fragility, but anti-fragility, the ability to grow stronger under stress. They evolve solutions we couldn't design, develop partnerships we couldn't predict, survive changes that would doom less flexible organisms. They are life's research and development department, constantly experimenting with new solutions to existence. In studying plankton, we study ourselves, the calcium in our bones, the iron in our blood, the phosphorus in our DNA, all cycled through plankton countless times before becoming us. We are temporary arrangements of atoms that plankton have been borrowing, using, and returning to the global pool for billions of years. In the most literal sense, we are made of plankton, animated by their oxygen, built from their recycled components. This connection imposes responsibilities. As we alter ocean chemistry and temperature at unprecedented rates, we challenge organisms that maintain our life support systems. Yet plankton ask nothing of us except that we understand our interdependence. They continue their ancient work photosynthesizing, recycling nutrients, producing oxygen regardless of our awareness or gratitude. Perhaps their greatest gift is perspective. In a world obsessed with size and speed and power, plankton demonstrate that the small and slow and patient inherit the earth. They show us that survival doesn't require dominance, that success can mean simply persisting, that true power lies in adaptation rather than resistance. As our journey through the invisible ocean ends, we return to that first breath. The oxygen entering your lungs connects you to a coccolithophore photosynthesizing in the Pacific, to a diatom dividing in the finding Atlantic, to cyanobacteria multiplying in every sea. Your exhaled carbon dioxide will eventually feed plankton you'll never see, in places you'll never visit, continuing cycles that began before continents took their current shape. We are passengers on a planet run by plankton. They are the understated majority, the invisible infrastructure, the ancient mariners who keep Earth habitable through their endless drift. Neither plant nor animal, but something more fundamental. They embody life's deepest strategy, not control but cooperation, with forces beyond control. Not resistance but resilience, not dominance but duration. Tonight, as darkness falls across the ocean, 10 billion tons of zooplankton begin their upward migration. Tomorrow, as the sun rises, phytoplankton will resume their transformation of light into life. And so it continues, the breathing of the sea, the pulse of the planet, the patient work of maintaining a living world, forever drifting, forever essential. Plankton remind us that on this water planet, the smallest things cast the longest shadows, and in surrender to currents lies the secret of eternal motion.